after we do all this stuff, any questions? Good. Since you've had the introduction to integrals, we can now talk about some more advanced concepts. It's a little bit better. I think it's funner. You might not think so at first, but you will. I promise, I'll brainwash you. Just like North Korea.
I've been looking forward to this my whole life. Follow.
Integration by substitution. Here's the point behind integration by substitution. What you're doing is trying to make a difficult integral easier. Remember from what I first told you, this was not a lie. In order to do an integral, it must fit in your integration table. Do you remember that? It has to. If it doesn't, you cannot do it. It's got to fit. So, what we try to do is either manipulate the inside of our integral somehow by distributing or dividing. Remember, like you did on your, hopefully you started your homework. You do this, manipulate trig functions, do all that, and make it fit somehow. What this is called, by the way, is a U substitution. So we'll be using the letter U. Let me give you a for instance on why we have this. And it's all about this problem. Write down that problem, we'll talk about it in a second. Firstly, ladies and gentlemen, does that problem fit your integration table exactly like it is? No. No, it's got some parentheses, it's got some stuff being multiplied. Knowing what you know right now, how would you do that?
Distribute.
Sure, and then it'd be fairly easy, right? It should be very easy. How about that?
They had a little bit longer.
You could, right? You could, though.
Yeah, it's still doable.
You could FOIL it out 3 times and then distribute your 2x, and you could do it.
There's someone with a hole like that.
Is that something you want to do? Only if you're crazy.
That's when you don't do the homework.
Yeah. That's when you go, Mr. Leonard, you failed me. You didn't teach me right. There's got to be a better way. And the better way is, this does not fit your integration table. For some of you who think this is possible, it's not. You can't distribute this in there. Okay, you can't do that. That's an exponent. The only thing you have to follow order operations, right? Exponents before multiplication. You have to do all that. I could teach you binomial expansion, but you'd be at the 50th row of Pascal's triangle with some pretty easy stuff, but still, it'd be longer than this board before you were done. Okay, it'd be crazy. Now, we're going to learn something different called integration by substitution. What it's going to allow us to do is substitute part of our integral for the letter U, thereby making a really hard integral really, really easy. You want to see how to do it? Of course, because it makes your life easier. I'm saving your life. I'm literally saving your life. That would take you like a year. It's going to take us 2 minutes. See, I've saved you however many minutes are in a year, -2. You're welcome. Here's your steps. The first thing you're going to do is pick U so that the integral is easier. I know that's vague. I know it's vague, but I'll give you some notes on that. You're trying to pick U so the integral is easier, not harder. Sometimes you'll pick the wrong U. It's okay. You'll know it in 10 seconds or less. Seriously. Pick U so the integral is easier.
Not right.
Yeah. Yes, you can pick U so that it becomes harder. Don't want to do that. But you'll know it. You'll get stuck. Here's 2 big hints. It's usually get it? Usually, it's usually the inside of something. It's usually the inside of something. And here's a must-have. The derivative is somewhere in the integral. The derivative of your u is somewhere in your integral already, okay? Disregarding constants. The constants don't matter. I'll teach you how to do stuff without constants. But the derivative, as far as the x's go, must be an integral.
Are we gonna elaborate further on that last one?
No, I'm just going to leave it to you.
That confuses me.
It's got to be an integral somewhere. Also make a note, this does not include constants. You don't really care so much about the constants. Disregard constants. Second step, that's where all the work happens, by the way. Second step, third step, fourth step, very easy. Second step is we're going to transform our integral from x dx to u du. So translate our x's to u's, our dx's to du's. Remember how your d whatever has to match your variable? If I'm going to put some u's up there, I can't have a dx anymore. That's not going to happen. I need to have a du. So I'm going to teach you how to do that too. Transform something in terms of x dx to something in terms of u du. After that, it will be in your integration table. If it's not, if you do another substitution or something else, or the integral is not possible using these methods, there are some that are not possible, and you can't do them. Or you can't do them with this integration by parts, or a trig substitution, or it's got to be in a table. There's things that we can't do in this class, right? We get to skim the surface. Step 3 will be solve your integral, so do integral. And step 4, notice what's happened here. I know it's very vague because I haven't shown you an example, but I need you to think through it, okay, with me. You're picking u. U's going to take the place of some x. Do you get that concept? It can take the place of some x. Therefore, when you go from dx to du, we got that down, then we're going to do our integral. But you're still going to be in terms of u. So you need to translate it back into terms of x. Does that make sense? You got to end with whatever variable you start with. So translate back to u. I think I said u, I meant x. Translate back to x. Okay, now for the good stuff. I'll show you how to do this problem. Now, what's the bad part in this integral? What's the bad part? Is the 2x a bad part? Not really. What's the bad part?
The 2 to 50.
Probably this part, right? That part. Now, when you're doing a u substitution, oftentimes you don't pick the whole thing, you pick the inside thing. You cover it up and you go, okay, if this were a u, could I still take the integral? And then here's what you do. You go, if this was a u, can you take the integral of u to the 50th? Mm-hmm. Absolutely. So don't take this as your integral, as your u, take just this little part. Here's why you take just that little part. You're going to have to take a derivative of this. You have to. So you want something where you take a derivative and it doesn't completely jack your problem up because you're going to have to put it back in your integral. Here's what we're talking about. I'm going to pick usually the inside, and it has to be such that the derivative is in your integral somewhere. So, derivative of this. You can do the derivative of that, right?
Yeah.
Take the derivative of that. What is it?
2x.
Is 2x in your integral?
Yeah.
It's going to work. No, it's going to work.
If it's not,
Now, if this was your u, your derivative would be 50 x squared plus 1 to the 49th power times 2x. Is that in your integral? No, that would be the wrong way to go. Here's why it has to be in your integral. You're going to see this in about 45 seconds. U equals x squared plus 1. Are you okay with the u? We pick the inside of something, also the derivative has to match up with something in your integral. Not necessarily constants, even if the 2, even if the 2 wasn't there, it would still be okay. The constant doesn't matter that much. Now, what you're going to need to do is take a derivative implicitly on both sides. So, if I take a derivative, the derivative of u is du. The derivative of this side is what?
2x.
2x and dx. By the way, here's why, if you want to know the why, because it looks weird right now. I guess most teachers don't show it this way, but I'll show you. If you took an integral with respect to x, what you get is du dx equals 2x, right? Solve for du. That's where we get, when you do that every time. So you need du and dx on different sides, so you can work it like that. If that makes sense to you, use that. Does it make sense to you? That would make sense to me. So, in either case, this is going to be du. This is going to be 2x dx. Raise your hand if you feel okay with that so far. Now, here's the cool part. We can do this like a double substitution. Not only are we going to substitute this part for some u, which we already are going to be able to do, but you can also substitute your dx if you can solve for dx. So, can you solve this for dx? Yes. How would you solve this for dx? If I divide by 2x, by the way, I know I teach this different from some of you who have had calculus before. I teach it a little different. I think this works better because you can actually see the simplification happen in this problem, okay? Are you still okay? You sure? So let me recap for a second. I guess it's more than 45 seconds, but now you'll see why you had to have your derivative somewhere in your integral. We look at this, we find the part that sucks. It's usually the inside of something, the derivative has to be there. Take that as your u, take a derivative of both sides. You're going to get a du every time. That's going to happen. You never have anything weird like 2u or 4u. That doesn't happen. You just take your derivative of u, you get du. Take your derivative of this side, you're going to get 2x and dx. Solve for dx. Raise your hand if you feel completely okay with this. Now you do the substitution. Instead of 2x plus 1, what do I put? Do I still have to the 50th power?
Yes.
Yes. This became my u to the 50th. Now check it out. My 2x is there, but what is my dx instead?
du.
Du over what?
2x.
Yes. U, 50th, 2x, dx. You got it? Hey, look at the two x's. Is one on numerator, one on denominator? This is basically like writing this. It's basically like writing 1 over 2x du, like that. Your two x's are gone. Gone. Integral of u to the 50th du. Notice how we have to have, this is important, this is why I make you guys write the d. Some people do integrals, they don't write the dx, they don't write the du. Do you see why you have to have that? It tells you what variable you're integrating with respect to. So if you didn't change to du and still had dx, this is not possible. You can't do it. So we had to change that. We had to write the du. Now can you take the integral of u to the 50th? Everybody should be able to do this. What is it?
First over 51.
Perfect. Actually, pretty easy. And?
Let's see.
Let's see. Right now, we're here. We're here. We translated. We're right here. You got to translate back into x. You see, we start with x's. We're now in terms of u. How much is your u? It's on the paper, right?
X squared plus 1.
Just put x squared plus 1 back there. X squared plus 1 in parentheses to the 50th power. Thank you. 51st power over 51 plus c. That's your integral. Does it actually work if you take a derivative? We probably do it in our head. It's kind of a simple one. You bring down the 51, gone, to the 50th power times the derivative inside because you're using a chain rule. That gives you 2x. that is the appropriate integral. That's it. Is it hard, medium, easy? It's gonna you have to understand it. You have to really understand it. One note that you need on this, you're going to notice that all of your x's must be gone before you can integrate. Do you see that? You cannot integrate with both x's and u's. It can't happen. So all your x's must disappear before you integrate.
Is that why the coefficients don't matter at the x?
Yes. Coefficients you can pull out in front of your integral, right? You're going to see that on some of the later examples. This is a very, very basic example. But I wanted to give this so you kind of understood it. So all of your x's must disappear.
And the only way you can do that is through the du over your x's that you remove.
No.
Oh, is there other method?
Yeah.
Okay.
I don't know how to spell eliminated either. There's two L's or one L?
One L.
Thoughts so.
Even those L's.
I don't like L's. Hence my name.
You got your name with two L's.
I just say it entered, not Leonard. Forget the L. Mr. Entered. Way better. Way better. It's tricky L's. I swear. You know, sometimes this U substitution stuff is pretty obvious until you get to trig, and then it becomes a little bit more cumbersome, but stick with the idea that your derivative has to appear somewhere, that you have to cross stuff out, you have to get rid of things, and then it helps you a lot. So in this one, hopefully we can kind of pick out the U already. Can you pick out the U already? When all else fails, if you're like, oh my gosh, I don't know, just pick the inside. Pick the inside, just the inside, not the exponent, the inside, and try it. What's it hurt you to try? You just take a derivative and see if you're right. I mean, it takes 10, 15 seconds, maybe tops, and that's better than doing nothing. So here, I'm definitely not gonna pick that. That really doesn't make it better. I want to pick this to make the inside go away, right? If I pick the inside, it goes away. I have u to the fifth, that's a piece of cake. Also, do you notice that the derivative of this is in your integral? What's the derivative of this?
2x.
No, the derivative is not 2x. The derivative of this is what?
3x squared.
3x squared. Ignore the 3 and say it again.
X squared.
Right there. You don't care about the 3, but the x squared has to be there. So u equals x cubed minus 4. Du equals 3x squared dx. I want you to solve for dx. Solve for dx. How do you solve for dx here? Divide by what? Okay, so do that. Give me a head nod. Look up at the board here. Give me a head nod if you're okay on getting down to that far. Are you? Yes? Yes? Okay, cool. Now it's time to do your substitution. As soon as you choose your u and you do the derivative thing and you solve for dx, you can substitute and see what you have. Look up here, is x squared still here? Yes, I didn't substitute in for that. Is this still here? What is this? To the, good, that fifth is still there. You never take that power. Oh my gosh, that'd be ridiculous, right? Because look, your derivative is right here. It'd have to show up in your integral in order for you to simplify it. And then instead of dx, I'm going to write do you see anything that simplifies here? What simplifies? What about the 3? Is the 3 on a numerator or denominator? So here's what I'm going to do for you. I'm going to say, well, that is a 3. It's basically 1/3, right? What can you do with constants? That's why constants don't matter. That's why you disregard the constants, because they really don't affect you in terms of x or u, right? It's just a number being multiplied. So this is 1/3. I know you can take the integral of that. That's u to the 6th over 6 plus c. We'll do one more step. We're going to multiply those fractions together. We're also going to insert back in what our u is equal to. That's x to the 3rd minus 4. So our final answer should be x to the 3rd minus 4 all to the 6th power over 18 plus c. Are we red light, yellow light, green light? Are we green light on this stuff?
Yeah.
Are we good to go? You sure? Are you okay on seeing where your u's coming from? It's probably the most important part, seeing that. After that, everything really falls into place as long as you follow these steps I've outlined for you. You take your derivative, you solve for dx. That's not hard, that's algebra. You plug it in, you cross some stuff out, pull out any constants, and then you'll have a very simple integral. It has to be simple. It has to fit in your table. If it doesn't, you either made a mistake or you can't do it. And that's the whole thing. Or you have to make a double substitution, which does happen occasionally. We might get to one. Let's keep rolling. Let's some good stuff going on so far. How about this?
No, what's right?
Now, if I gave you that integral at the beginning of integrals, like last section, you'd be stuck, right? There's no way you're going about doing that because that does not fit in your integration table. That's sine of x to the fourth. That's times 2x cubed. You can't separate integrals by multiplication. You can't take the integral of this, the integral of this, and the integral of that and think you're going to be right. It's not going to happen. The only thing we have left to us is substitution. That's all you get in this class. You get either it somehow fits, you have to make it fit, or you get substitution. That's it. There's no other method that we have in 4A, in first semester calculus. There's only two options you got. So let's try to pick something for our U. Why don't you write down what you think is U? Don't say it out loud. Why don't you write down what you think would be a good U? Remember the two criteria. It's usually inside of something, not the whole thing, but inside of something, and the derivative must be there. Gotta be there. So question, should I pick sine? What's the derivative of sine? Do you see it? Then sine's not the right choice. How about 2x to the third? Is it inside of something? Not a good choice. Also, the derivative is an x squared. Do I see an x squared anywhere up there? That's my good choice. Just x to the fourth. Did you pick x to the fourth? Okay, so put it off to the side. You have to show your work. Be organized. Trust me, be organized with this. Because doing integration by parts later in your next semester, you're going to have to be very organized with it. Otherwise, you're going to lose stuff. Because integration by parts, sometimes you integrate by parts, which is, they'll teach you that then. Then you have to use substitution on both of them. It gets crazy if you're not organized. Okay, we have x to the fourth. Y'all tell me, what's the next step that we do? Okay, do it. Hopefully you still remember how to take derivatives, right? That's why we have to cover derivatives for integrals for this stuff. Okay, what's your next step after you do your derivative? Don't forget the cube. That's going to be du over 4x cubed equals dx. Still okay so far? Now you substitute for whatever you've picked. The only things you substitute for are your u and your dx. Everything else stays there until you cross it out. So let me ask you this question. Does the 2x cubed stay there? Yep. Does the sign stay there? Does the x to the fourth stay there? What does that become? That's your u. Very good. Does your dx stay there? How much is your dx equal to? Show of hands. How many people feel okay with this example? So trig function, yes. Hard, not really. Pick a u. It becomes easier. Why does it become easier? What happens now? The x cubes are gonzo, right? They're done. That's great. That has to happen, right? You have to get rid of your x's because now you're in terms of u. You got to be in terms of u.
And then you can pull your 4 outside that.
Pull your 4 outside along with what other number?
And your 2.
The 2 over 4. That's going to give you 1/2. Do you see the 1/2 that I'm talking about? So this is 2 over 4. I can show you both steps if you want. 2 over 4 sine u du. That's 1/2 sine u du. Now don't say it out loud because you need the practice, trust me. I want you on your paper to put down the integral of sine u. Don't say it out loud. Try it on your own. I know you're all going to give me cosine, but what I'm looking for is whether it's positive cosine or negative cosine. Hopefully, you put negative cosine. Did you put negative cosine?
Yes.
Good for you. If you put positive cosine, check it again. You need to be able to take a derivative of it, and it gives you sine. So this is negative cosine u plus. Are you okay with this so far? What's the last thing that we do?
Translate back to there.
Yeah. Maybe make it prettier, that negative. I don't like that in there. I want to make this negative 1/2 cosine u, but u is x to the fourth. So I'm going to make this negative 1/2 cosine x to the fourth plus c. That's how it should look at the end of your problem. Or if you wanted to put this over 2, you could do that. What you can't do is this. Please look at the board. Please notice that 1/2 never ever goes inside an angle. This is never x to the fourth over 2. You can't do that. You can't break that angle relationship. This is not multiplication. It's cosine of something, of some angle. So you can't do any operations inside of that. You can't pull anything out unless you use angle formulas or something like that. We'll start one more. I want to show you something here real quick. So we have about, 30, 45 seconds left. Now this.
I don't know. So,
This one looks pretty darn nasty, yeah?
Yeah.
But let's really think about what's going on here. This is going to help you on some of your homeworks, all right? This is going to really help you, actually. What's the bracket mean? Well, what's it mean?
Everything's together.
Take the integral of that, right? Of all the stuff inside. Now, tell me something you do with integrals as far as it relates to this problem.
Separate that.
Say it louder.
You can separate them by the addition sign.
Or subtraction, right? The only thing you can't touch is multiplication and division. So I could actually separate these two things.
man, I don't know. The brackets really messed me up. This probably don't know what to do with, really. This one is just x to the -1 over -1. Yeah, this side, it's interesting.
Get 1 over x squared plus dx plus secant squared pi x dx. That makes it a whole lot easier. Why does it make a whole lot easier? Well look, that's basic. That's in your table. Make it x to the -2, do the problem. This, that's integration by substitution. Sure, you substitute your u equals pi x, do the same thing.
So what does this help them? That didn't really do anything.
So that's actually a little bit easier. Does it make sense to you? So when you have the addition subtraction, break it up. Before you start doing a substitution, break it up. Sometimes if you tried substitution here, it's not going to work because you have this relationship. That'd be a bad thing. You wouldn't want to do it there. So break it up by addition subtraction, then do your substitution on the individual parts. Now,
Are we
if
just
you
not going to go
remember-
over that? I don't know how to do it. Unfortunate.
We're doing integration.
Yeah, still don't know how to do this. Yeah, no. I don't know.
Which is basically find an antiderivative and in other words, find the area underneath the curve or find the area function of a curve. And we're doing a special case of integration where it doesn't necessarily fit into the integration table exactly, so we use some sort of substitution, typically a u substitution, to make it fit. It's kind of like making this thing work for us, which is great. Now, I gave you a couple hints on how to do this. Number one hint is you're usually picking the inside of a function, the inside part. It's typically in parentheses or underneath a square root or something to a power. You don't pick the whole thing, you just pick part of the thing, the part that's actually giving you a problem. For instance, in this case, the part that is not actually in the integration table. So if I'm looking at this, I know cosine's there, but it says cosine x, not 5x. So what I would pick for the u in this case is
5x.
the 5x, yeah, that's the inside. Also, we'd say the derivative of your u typically must show up in the integral somewhere, disregarding constants. So let me ask you this: what's the question? What's the derivative of 5x? Now, we don't care about the 5 being up there because that's a constant. We'll be able to pull that out as 1/5. So basically, just our x's have to match up.
Why
So
would you
again,
do
our
that
idea
for?
was, let's make a u substitution so that our integral will ultimately fit into our integration table. If it fits, then we can do it. If it doesn't fit, we basically can't do it right now. Now, what did we do after we took the substitution? What's the next step?
Find the derivative of our u.
Okay, so derivative of both sides, basically it's implicit differentiation where we're keeping the dx on the right-hand side. So here we'll have du, here we'll have 5 dx, and I've told you to solve for dx. Some people do this differently, some people don't solve for dx, some people try to substitute in for, make it something x dx and substitute in for du. I prefer solving for dx, it just makes it a little bit easier for us. So if we divide both sides by 5, we have du over 5 equals dx. That lets us make our substitution. So we go, all right, the cosine doesn't change, but the 5x, I'm going to let that become u, and I'm going to let dx become du over 5. The key thing for us
Oh
is
wait,
that
I see. Okay. So take out the 1/5. Take the integral of cos u du. This is would be sine u. So sine 5x over 5 plus c. Alright, that makes sense.
in order to take an integration, do an integral, two things must happen. It's got to fit your table, and the variables have to match. So our respect to that variable must be the only variable you see. If there's x's and u's, you've done something wrong, or you haven't gone very far enough. So something has to take place where you have one variable, and that's the variable you're talking about. You with me on this so far? Now, the over 5, what can I do with that over 5? That's why we disregard the constants. We really don't care about those. It's all about the variables. So this over 5 means 1/5 cosine u du. That will be 1/5. All right, folks, let's do the integral of cosine u. Don't say it out loud. I'll give you just a second to think about it. Try to get in your head. Before someone says it, okay? So think as I've been talking and rambling to keep you guys from talking. Have you thought about the integral of cosine u? Of course it's going to be something to do with sine. Is it positive sine or negative sine?
Negative.
Oh, you guys are guessing now. Don't guess at the stuff. If you said negative sign, take the derivative of negative sign. It would give you negative cosine. That is not what we have right there. The derivative of sine gives you cosine, yes, yes, and that's the correct integral, therefore. Does that make sense? So be careful. It's all about the signs with your trig. It's never. I mean, no one's ever going to go tangent. Yay! No one's ever going to make that mistake. You're all going to give me sine, right? It just depends on whether you get the sign right. Right? Okay. Anyway, we're almost done. There's one more thing that we have to do. We didn't start in terms of u, so we can't leave it in terms of u. We're going to translate this back to x's. Use the same substitution you just made. So our answer, our integral, will be 1/5 sine of 5x. And of course, we got that plus c at the back end saying that could be any constant and still work as a function. So that I take a derivative of it, gives me back my cosine 5x. By the way, can you check your work? Absolutely. Take a simple derivative. Do you see the chain rule coming back at you? The 1/5 times the 5 from that chain rule, it's gone. You got your cosine 5x. How many will feel okay with our example? That's kind of a refresher from last time since we had a weekend in between here. Now let's do one where I have you do this completely on your own. See if you can do this, and then I'll show you how to finally finish that example I had you look at last time.